Orbital Theory. So what is molecular orbital theory? I don't really know, but I know what it helps you do. So when it comes to molecular orbital theory, it helps you determine the stability of the compound through bond order, and it also helps you identify like bonding and anti-bonding and all that bullshit. Okay, so basically let me try to do a visual of anti-bonding. Whew. That's a lot. So this is a positive and this is a negative, represented by two different colors. That's how it'll be on the fucking the presentation. Equals, you're gonna have, when they anti-bond, it's gonna look like this and it's gonna look like this. Okay, this is what it's gonna look like. It's not pretty, but this is destructive interference. This is gonna be a long ass video because I'm slow, but it's okay. Destructive interference. Watch this in like 0.5 speed. So remember that original time when we were learning quantum mechanics where he did this? So basically it's a positive, it's a negative. When they combine together, it's gonna form 0. So that's anti-bonding. So now you know, when it comes to anti-bonding, you know how in regular bonding, when we're doing Lewis structures, it's usually like you do 2 H atoms and then they come together, they form this bond. Well, when it comes to anti-bonding, the electrons are not inside, instead they are outside. Okay, so with this is just conceptual. This is not what you need for the exam, but this is conceptual for you to understand. So with this, you have to know that there is a force represented by F here. The force is attracted to this electron. We're gonna just put, the force is attracted to this electron, but the force is also repelled by this hydrogen right here, because, you know, it doesn't like it. So the force is going towards this way, right? But then there's another force that's attracted to this electron, right? So that there's going to be a tiny, just a tiny bit, because it's pretty far, just a tiny bit. So same thing happens over here, where there's a force attracted to this electron. There's a force that's going away from this hydrogen for this one, and there's a tiny force attracted to this electron for this one. So when you combine everything together, there is more, it's going to have a net repulsive force, because there's more things trying to repel it than there's more things trying to bond it or attract, you know, for these two atoms right here. So that is anti-bonding. And now we're going to look at bonding. Okay, and bonding is constructive interference. I don't know how to spell. Interference. Oh my gosh. Okay. So in constructive interference, we have something like this. We have something like this as well. And this is a positive, positive. This will equal a big ass, you know, obviously. So that's bonding. And imagine a circle, another circle. It makes a thick circle. That's bonding. So now with bonding, remember, the electrons are actually in between the two atoms. So let's represent it as, this is the atom. This plus sign is only to represent that hydrogen has a positive charge. At least that's what I heard from the video I watched. Anyway, so there's going to be electrons inside, right? So there's going to be an attraction over here to this one, right? This is going to have an attraction. This is going to have a repulsion from this one. But the repulsion is not going to be that much, because, you know, this is behind the electron. This is pretty far. It's kind of like here. Over here, where, you know, this was pretty far, so the attraction towards it was pretty small. So that'll be the same thing here. The repulsion towards this would be pretty small. And then the attraction to this one is going to be pretty big as well, because it's pretty close. And then same thing over here, the attraction to this electron, the attraction to this electron, and the repulsion from this other atom is going to be pretty small. So it's going to have a net attractive force because there are more things trying to bond it than more things trying to anti-bond it. So that is just that conceptual thing, right? That's the first part you need to know. Now, another thing, I recommend you like either skip over the first part that I just said, or really try to fast forward. I really hope. I hope this was recording the whole time. Oh God. Okay, it is. All right. Now we're gonna go into the good stuff. Okay. So this is what you've all been waiting for. Now, this is the regular way to do this shit. Energy. And we're going to do this for the hydrogen atom. We're going to do this for H2. You're going to see stuff like this on the assignment. It's like C2 minus H2. I'll explain everything. I'll solve everything. I have time. I need to go to sleep, but I have time. I need to wake up at 9 a.m., but it's okay. It's okay. Anyway, so now this, right? This is what it will always look like. I can't explain to you why it is the way it is. That's just what it's going to look like. Now, hydrogen's electron configuration, right, is 1s2, right? Actually, no, it's 1s1, my bad. It's 1s1, right? That 1 is also the amount of valence electrons that it has. Okay? Sorry, hydrogen valence equals 1. So that 1, right? So since we have two H's, we're going to look at it as 1s1 and 1s1. Electron configuration is very important for drawing molecular. This is what we call a molecular orbital diagram. Okay? So we're going to have, you have to draw the electron configuration for both of them. So it's two hydrogens that are about to bond. So you have to draw the electron configuration for each one. And there's going to be tricks where they will give you something like O2 minus, where you have to realize that it's O. O is the first electron configuration, and then you have to do the electron configuration for O minus, which means you have to remove an atom. Add one. My bad. Add one. But we'll get into that later. Sorry. So now just know that you're always going to have this weird thing, okay? When you draw an electron configuration. Now, the bottom is the bonding. So we're going to put this sigma because it's just one bond. Sigma 1s, because the electron configuration 1s, yeah. That's the highest energy level we can go to for now that we know of. Okay, so 1sa, just represented by A and B, just because it's like hydrogen, first hydrogen, second hydrogen. That's all it represents. That's literally it. So over here is the anti-bonding. Anytime you see the star, it means anti-bonding. Okay, so on the upper level is anti-bonding. Anti-bonding will always be at a higher energy level. Okay, this is a higher energy level than the bonding level. Okay, so now, guess what? This one, right? This hydrogen has one valence electron, and you're going to represent that by putting it here. This hydrogen has one valence electron, so you're going to represent that by putting that over here, right? Now, what I learned from the video is that it is easier for it to fall to a lower energy level than it is to jump to a higher energy level. Just like it is easier to go down a mountain than it is to climb up a mountain, right? So what you're going to do is you're going to put those two here, okay? And let me not put the arrows, but basically that's going to be represented by it can't be two arrows up. It's just going to be like this, okay? So as you can see, we have now completed the molecular orbital diagram because this is as far as it goes. It's only 1s. For hydrogen, this is the easiest one to do, and we're going to go into the harder ones later. So to calculate the bond order, we have to remember it's the amount of bonding electrons minus the amount of anti-bonding electrons divided by 2. How many bonding electrons do we have? This is the level of bonding. We have 2 bonding electrons. 2. Minus how many anti-bonding electrons do we have? We have 0. Divided by 2 equals 2 over 2, which is 1. So that is the bond order for an H2 molecule. Okay? Now, let's get into the harder stuff. So you're going to probably see this frequently on the... What the fuck is that? You're going to probably see this frequently on the exam. I mean, not exam, but on the assignments. But let's do one for C2 minus. Okay? Now, one thing you have to remember is... Let me tell you something. So this is a rule that you're going to have to learn. You're going to have to know this. There are 2 types of diagrams for 2p orbitals. We're going to be dealing with 2p orbitals when it comes to molecular orbital diagrams the most, because that is actually as far as it can go. The person who created this molecular orbital theory, it only goes for about a certain amount of second period elements, actually. So we don't have to worry about other shit unless they make it more complicated. For the 2p molecular orbital diagram, because this is just for the S. For the S is always going to give you like 1, 2, 3, 4. That is going to be for S orbitals. So 2s is going to look like that as well. But for the p orbitals, right? For the p, this is how it's going to look. And be prepared. Okay, there's 2 types of p. So there's the first one. 1, 2, 3. 1, 2, 3. 1, 2. Let me move this. We need space. 3. Remember this image. 1, 2, 3. You're gonna have to study this. So this is gonna be represented by like little dots or whatever. Just gonna just to show you, like, the professor is probably gonna like they're probably gonna need points to be able to do that. The fuck. Some bullshit like this. Okay, don't worry about that. But just know it's 1, 2, 3, 1, 2, 3. This represents the pi bonds. This represents a sigma bond. Pi bonds, sigma bond. Oh, shit. What the fuck is that? Okay. Let me check if I'm still recording. Okay. All right. I hope that my audio was good enough. Okay. So now, since we've seen this... Hold on. Is my audio good enough? Yes. Okay. Since we see this, right, one thing we have to realize is that there's 2 types. This is the first type. And this is for elements with protons, or should I say atomic numbers, that are less than 8. Okay, so like your carbons, your nitrogens, your fucking lithiums, you know, shit like that. Your hydrogen. And this, the other one, is for the ones that are greater than or equal to 8. So from oxygen and above. Okay. So, now here's what we're gonna do. This is the second type. The second type is the one that was shown in class. Probably gonna be on somebody's slide. What else? Oh yeah. 1, 2, 3, 4, 5, 6. Do you know why it's 3 on both sides? Because this is a p orbital and p has 3 levels. Also, this is px, this is py, and this is pz. Px, py, pz. Just so you know, because on the active homework, they're going to be on like px, py, pz, p this, and you're going to be confused. Just know that that's what those mean. So yeah, that's all you got to know. Also, there's also like x and y here, some shit. Basically that, yeah. So this is going to be a sigma bond because it's on its own. This is going to be a sigma bond, asterisk, it's anti-bonding. Remember, it's anti-bonding, asterisk, start. Okay, sorry, pi, asterisk, whatever the fuck, asterisk. It's gonna be sigma, pi, pi. Now, this way of drawing it, right? See the difference? The only difference is here and here. It's just going to look different. This is you're going to write the sigma bond first, then pi if the atomic number is 8 or greater than 8. And for this one, oops, it's just going to be pi bonds first if it's less than 8. You're going to be dealing with atoms that are less than 8 on the homework. So you're probably going to need to use this one, actually. So just draw the little, you know, whatever. Fuck it. I don't fucking know what I'm doing. This, whatever. So annoying. I don't even know how to start. Fuck it. Okay. So that's what you have to know, right? So now to draw the molecular orbital diagram for C2, first thing we have to know is we need to know what kind of molecular orbital diagram we're drawing. So the amount of protons that C has, the atomic number is 6. And for the ones that are less than 8, we're going to draw it this way. So I'm just going to copy and paste because I really don't feel like doing this shit again. Okay, copy. All right, cool. Cool. Okay. So the first thing we're going to draw is a 2s because we have to know the electron configuration. The electron configuration is 2s. This is for the valence electron, so don't mind if I don't start from 1. 2s, 2p, 2, right? But remember, it's a C2 minus. So you have to know the electron configuration for C and C minus. Because if it was C2 minus, then you would have to draw for C minus, because that would add up to like C2 minus, right? So we're just going to do, they invented their own math. Fuck it. Chemistry's weird. So C plus C minus, or C times C minus in this particular case, would be C this, right? So the electron configuration for C is 2s squared, 2p squared. The electron configuration for C minus is 2s squared, 2p1. 2p3. Because we're adding an electron, right? We're adding an electron. Now, one other thing you have to do, if I was a teacher, I would have been able to explain this shit better, but I don't know. One thing you have to do is add up the amount of electrons. So how many electrons are in both of these? So C has 4 valence electrons, right? We have to add up how many valence electrons? 4. The other C will have 4 valence electrons plus 1, 9. So when you count your shit, it should be 9 total, right? So this is what we've decided on. This is what we're going to implement into this. So remember, s orbitals and p orbitals are on totally different levels. So what you have to do is first you have to draw the molecular orbital diagram for the 2s2. Then you have to draw for the 2p3. That's why this is so time consuming. And you have to be a professional to be able to like not do it without drawing it all out. So it's going to take your time on the exam. Okay? But being slower and accurate is better than being fast and inaccurate. Okay? So just remember that. So take your time. So now we're going to draw for the 2s. I'm just saying, like, that's just how life is. Okay, so we're going to label it 2s, obviously, but we're going to put that sigma. And then we're going to put a sigma asterisk 2s. That's just the professional way of doing it. If you want to get all your points, I know it sucks. Life happens. Okay, this is for the 2s, and this is going to be for the 2p. Because remember, p orbitals look like this, s orbitals look like this. Okay. So now that we're doing that, it's going to be this way. How many electrons are in the 2s orbital for both of them? It's going to be 2, right? So this is the C, this is the C minus. Let's always make that available. So 2 here, 1, 2, 2 here, 1, 2. Remember, it always falls to the lower energy level first. We have to follow Hund's rule. So start filling up from the bottom. So we're going to fill up all these 4 up. It's going to be 1, 2, 3, 4, because we have 4 total. right? So now we're going to leave that there. And remember how many, this is for a C, this is for a C minus, okay? So how many p electrons does it have? It has 2 p electrons, sorry, C minus. So it's going to be represented by 1, 2. How many p electrons does C minus have? It has 3, so it's going to be 1, 2, 3. Now everything's going to fall, right? Because it goes from the lower energy over. Just count how many it is. 1, 2, 3, 4, 5. Just count that and just like fill it up. Follow Han's rule. 2, 3. My bad. It has to fill up the lower energy level first. 1, 2, 3, 4. I know I'm doing the opposite way. Don't worry about that. 4, 5. Okay. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Boom. So now to calculate the bond order, we have to remember it's the amount of bonding electrons minus anti-bonding electrons over 2. How many bonding electrons do we have total? 1, 2, 3, 4, 5, 6, 7. Never forget that one. So we have 7, right? How many anti-bonding electrons do we have? 1, 2. 7 minus 2 over 2 equals 5 over 2. Okay. I forgot what 5 over 2 is, child. Let me Google that shit. You probably know the math. It's like 11. I'm tired. Okay, that's 2.5. So the bond order, the bond order for C2 minus is 2.5. Okay, that is how you do that. So there are times when they might give you something like F2 or F2, oh shit, F2 minus. Or they might give you an F. Or even fucking NH. Who knows? But all you have to know is the electron configuration for both. Okay? So in one of the actives, it said Cn. It actually drew it out for you. But it said Cn minus. So now you have to calculate the amount in C, the amount in N, plus the additional electron they gave you. C has 4 valence electrons, N has 5, plus 1 equals 10. So when you count everything out, it has to be 10. So if I count everything out here, it has to be 9, right? Because this is 9. And when I say out, I mean like literally on the outside and on the inside. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Everything on the inside has to be 9. Everything on the outside has to be 9. Just so you know. Okay, that's how you know you're doing a good job. So remember, if it's greater than 8, greater than or equal to 8, you're going to use this version where you put the sigma bond first, then the pi bonds. If it's less than 8, which you're regularly going to use, you're going to put the pi bonds first, then the sigma bond. Also, one thing you have to remember, and you don't have to, but if you, just to be like a boss at this, just to know, let's say we have carbon and fluorine, right? And you're trying to find out the molecular orbital diagram for carbon and fluorine. One thing you have to know, control negative atom is going to be on the lower energy level. It's gonna be, it's gonna be on a lower energy level. Now, what I mean by that is not that like you're gonna fill it in first. It just means that it's going to look different. Okay, it's going to look different. It has to be reflected. If they, let's say in the next exam, they like express this, you have to draw it in that way. Okay, so let's draw for CF. How many valence electrons? It's gonna be 4 plus 7 equals, is CF, let me see if CF molecule. Okay, it's just CF. I just wanted to make sure it wasn't like a CF minus or anything like that. So it's just going to be CF, 4 plus 7, 11 per. So it's going to have 11 electrons, valence electrons by the time we finish. Okay, so what I'm going to do is copy and paste because I don't have time for this bullshit. Okay. Copy. paste. Okay. Let's just erase whatever we've done so far. Because life is good, life is good. Okay. So the electron configuration for, because fluorine is 9, right? So it has about 7 valence. Oh god, that's so annoying. 2s2, 2p5, I think, right? I hope so. Hope the fuck so. No time for this bullshit. But anyway, so first we figure out the electron configuration. For carbon, it's 2s2, 2p2, right? 4 valence electrons. And for fluorine, I'm just counting the valence electrons. 2s2, 2p5, which adds up to 7. Okay? So now that we know that, let's draw for the 2s. Both of their 2s's are filled up. Okay? This is for carbon, this is for fluorine. Both their 2s's are going to be filled up. So we're going to have the same shit, just fill it up with 4. You have 4, 1, 2, 3, 4. So if you notice the pattern, when the 2s2 is filled up, it means that the entire thing is going to be filled up. Okay, it's like a base. It's like a base. All about that base. So now, let's see something. Remember the rule I told you that it is, if it's greater than or equal to 8, it's going to have this kind, right? And if it is less than 8, less than 8, is going to have this kind, right? So when I told you that, when we have two that are totally different, right? C literally has 4 valence electrons. C is 6, that's 6 protons. I am so sorry, disregard what the fuck I said. So the whole thing about that is Z actual has to be greater than or equal to 8 in order for it to have that. Z actual just equals like your atomic number. So the atomic number for carbon is 6. The atomic number for fluorine is 9, right? So we're over here like, dang, what do we do now since they're so different, right? So which one do we fucking use? We don't know that. So what you're actually going to do is you're going to find the average. Yes, I know. This is just for people who want to be like, I don't know if they're going to put this on an example if you want to be really good at this. So the average of this is, 6 plus 9 over 2. 6 plus 9, what the fuck is 6 plus 9? 15 over 2. 2 into 14, so it'll be 7.5. Okay, 7.5 is less than 8, which means we're going to use this diagram. Okay, so let's remove all that math. Actually, let's keep the math. Fuck it. So we're going to use that diagram. So I'm going to copy and paste it because, good notes. Okay. And yeah, it's just to make it easier. Just like have this on in your notes as just like a, what do you call it? A control. So that anytime you need to draw, you don't have to draw the whole thing. You just copy and paste whichever version you want. Okay. So now we're going to label it C on this side and F on this side because it's CF. So now, I'm stressing out, child. I'm stressing out. Ooh, I'm stressing out. Yeah. So I forgot, like, for officials, you have to put it as, like, 2P, 2P, 2P to get full points, 2P, asterisk 2P, 2P. That's so annoying. Perfectionist. Okay. Okay. So now we have to go back to business, right? How many valence electrons does carbon have in the p orbital? It has 2 in the p orbital. So we're going to put it up, 2. How many does fluorine have? Fluorine has 5. So we're going to put 1, 2, 3, 4, 5. Now we're going to start dropping it low. So just like count how many it is. 1, 2, 3, 4, 5, 6, 7. So it's just going to be 7, okay? Just count, you could just look up here and count it. 7. We're just going to fill up 7 orbitals. Don't even think about both sides. Just know that this is just, courtesy, to know what you're doing. That's it. So 7, 1, 2, 3, 4, 5, 6, 7. So this is important because they're going to ask you what is the most habitated orbital? Don't worry about it. Don't worry about it. Don't worry about it. Don't worry about it. Just don't worry about it. I'll ask you on the active, what is the HOMO? Let me actually Google what HOMO is. HOMO chemistry. The HOMO is the highest occupied molecular orbital. I know it doesn't sound right because it sounds like discrimination, but yeah, that is the highest occupied molecular orbital. So that's the reason why it is important for you to do it in the right way, you know, using Hund's rule, because in the active, it's going to ask you what is the highest occupied. When it says highest occupied, it is not referring to the one that has the most. It is not referring to that. So please do not pick that. It is referring to literally the level it is. The highest occupied orbital in this case is 2p. It is pi 2p x. This is x. This is y. This is what I've noticed. Okay. So this is 2 pi x. It's literally going to give you stuff like this on the active. And it's going to say, what is the highest occupied molecular orbital? It is literally the one on the highest energy level that has like a fucking like of any electron. That is what it is. Okay. So it would be pi 2px. All right. So let's continue with this so we can find the bond order. All right. So now that we fill this up, bond order, remember, equals the amount of bonding electrons minus the amount of anti-bonding electrons over 2. So what is the amount of bonding electrons here? The amount of bonding electrons here, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Is 8. I just don't like dots on my shit. It's 8, okay, minus the amount of anti-bonding electrons. 1, 2, 3. Yay, I hope that's it. Over 2. What's 8 minus 3, child? 5 over 2 equals 2.5. Okay. You can Google this shit. I don't know if I'm right. You can Google it, but I'm pretty sure I did it right. So let's say bond order for CF. CF molecule bond. I don't know why they're trying to mess with me right now. Yeah, it is 2.5. Okay, so do you know one thing I missed? So one thing I missed in this whole thing to show you, which is literally the whole fucking point. Why did I miss that? One thing I missed to show you, right? Hold on, let me keep this. Let me keep this shit. One thing I missed to show you is that when it comes to drawing this, it's actually not on the same level. Because the whole point of me starting this, because I usually go off topic, is that this is more, where is it at? Fluorine is more electronegative, right? The most electronegative atom is the lowest energy level. So I forgot to tell you, you're going to draw it in a weird way. I know. It's okay. I know. You don't have to. They might accept it, but it's going to be weird. So let's just do this. Okay, so it's going to be like this. Child, I don't even know how to draw this shit. I don't care. It's so fucking weird. Come on. So just imagine this is like, like this, right? So imagine this like this. You're gonna have the same shit. 1, 2. You're gonna have the same shit. 1, 2, 1. The only difference. Oh, oops. Hold on. What? I know it's confusing, but just like stay with me, stay with me, stay with me, stay with me, stay with me. It's weird, I know. Stay with me, 'cause you're all I need. They say love, it's clear to see. Oh, my bad. This gotta be in a lower. Keep going. Getting lower so I can like do this bullshit. Okay, anyway, so it's gonna look like this. Fluorine is more electronegative, right? Because fluorine is more electronegative, it's gonna be at a lower energy level than carbon. So if you Google pictures, literally Google pictures of the molecular orbital diagram for CF, and you're gonna see that weird like zigzaggy, like trapezoidish type of look when it comes to that. So yeah. So I'll literally, let me literally Google it. I hope I don't. Well, okay, I'm good. CF molecular. I type really slow, so just. It's going to look weird. This is inorganic chemistry for some reason. So see how this is like balanced? So I guess that could be accepted. Where's the other shit, bro? Bro, they literally just had it. Are you fucking kidding me? Stop. Okay, it's right here. Sorry. So if it's more electronegative, it's going to look in a slanted way. You know, just like, I'm just going to save that to my... How do you say it? Okay. Save photos. Okay. Yeah. This is also for CO. It's going to look like that as well. See how it's like weird and slanted? Yeah, that's life, bro. See what I was telling you about the pies being at the bottom first? That is because the average of these two is less than 8. C has 4. Oxygen has 6. The average of those two. 4 plus 6 is 10. Divided by 2 is 5. Less than 8. So it has to look like this. Okay? And if it's this one, it means that the average was greater than 8. It was equal to or greater than 8. This is just for oxygen. I don't know what the fuck A is, but this is just for oxygen. Oxygen is 8, so if it's 8 or greater than 8, it's going to look like that. Look at this over here. Yeah, that's balanced. That's very balanced. I don't think that was just for oxygen. I think it's for oxygen and something else. That's why there was like a slanted, because the most electronegative atom was at the lower energy level. So yeah, that is definitely what it looks like. Also, my molecular orbital diagram notes for this look so aesthetic and so pretty, so I'll send it to y'all. But yeah, watch my video. Watch my YouTube videos. This is what we did in class. So now, remember when we went to workshop, this image now makes sense to me. Because when she was explaining it, I was like, what? But then I watched the videos. I watched more than Organic Chem Tutor. I watched like multiple videos on molecular orbital diagram as they solved it. And it made more sense because Organic Chem, he explains to you the basics. And like for helium and like hydrogen. But you need to know stuff for like atoms that look different. You know, like what does that look like? N2 plus, O2 plus. You know, don't remember, this is irrelevant. This statement is irrelevant. So don't focus on this, because literally N2 has a greater bond order than N2 minus. Because it said that the removal of an electron, it decreases the bond order, right? So you would think that like, since N2 plus, it's removing an electron, the bond order is going to be small. N2 minus, and just N2, N2, the bond order is going to be bigger, right? Because they didn't remove an electron. And if they add an electron, N2 minus is going to have a bigger bond order. It's going to go in that way, you know. N2 is less than. No, that's absolutely not it. Do not look at this. Do not try to write this down as your notes. In reality, N2, the bond order of N2, when you calculate it using what I told you, the molecular orbital diagram, it's going to be 2s2. Try this on your own. 2s2 and 2p3. And try N2 minus, which is going to be N equals and N minus equals. It's going to be 2s2, 2p3, 2p4. Do not worry about changing it from 1 to 5. Don't worry about changing it from S to like P5. Don't do that. We don't do that molecular orbit diagram. Just fuck it. We just put it in like that. Put it in with the 4. Because I tried doing that before, it fucked me up. So don't ever do that. Regular electron configuration, you can do that. But for molecular orbital diagram, you need it to be in the regular way. Don't change anything. Okay? So you're going to apply this, you're going to draw this, and that's your challenge. You will notice that the bond order of this is greater than the bond order of this, which means that that statement, this statement, that removal, it decreases, which means if you add some, it increases it, is false. So I'm going to remove this. It was Google that told me this. Google lied. So this is going to be your practice. Good luck on the exam. This is the feedback from active. It's kind of a lie because that's kind of the same thing they told us here, but it didn't do it because like N2 bond order is greater than N2 minus. So you can figure out why that is yourself. I did O2 plus. Yeah. O22 plus. O22 plus, don't get it confused. It means different O's. It means the O's add 1, okay? When it says like 2 minus or 2 plus, it does not mean you should remove the electron. Was it 2p4? It does not mean you should remove 2 from each one, right? When you put out it does not mean you should do that. It doesn't mean you should remove 2 and it'll be 2s2, 2s2. No, fuck no. No. It means you remove 1 from each. That's the